Assalamualaikum. My name is Malia Rahman. Last three digit of my ID is 524. Today we are presenting Turing machine, an important topic of theory of computation. Meet our team: Jahid Patwari, Mahir Faisal, Orpita Debnath, Faisal Hussain Khan. What is Turing machine? A Turing machine is a theoretical model of a computer. It can read, write, and move on an infinite tape. Because of unlimited tape, it is a very powerful. It can perform any computation that a real computer can do. Formal definition of Turing machine. A Turing machine is defined as seven tuples: M, Q set of state, summation input alphabet, gamma type alphabet includes blank, alpha transmission function, q not start state, q accept state, q reject state. Now I would like to call my next teammate Orpita Devnath to present the next slide. My name is Orpita Devnath. My ID is 241-15525. Now I will explain why the Turing machine is better than other computational model. If we compare machines, finite automata have no memory. Push-down automata have limit memory using a stack. But Turing machine have unlimited memory in the form of an infinite trap. That is why Turing machine can solve all computable problem while uh, FA and PDA cannot. Input tab and fundamental Turing machine components. Input tab, input symbol placed on a tab on parcel. Tab continues infinite to the right with blanks. Head starts on the first input symbol. Tab components, it starts head, reads, writes, moves left and right. State, start, q naught, q1, q2, q accept, q reject. Transmission function decided, next symbol, symbol to write and movement. General Turing machine transmission logic. This slide explains a Turing machine works step by step. The machine reads on symbol from the tape at a time based on the current state and the symbol read. It decides three things: what symbol to write, whether to move left or right, and which state to go to next. The process is written as mm, new symbol direction, then next state. This transition rule acts as the brain of the Turing machines and helps it reach and accept or reject state. Thank you. Now I would like to call my next teammate Jahid to explain the next part.
Assalamu alaikum sir, my name is Jahid Patwari and my ID is 241-15240. Now we will see example 1. A Turing machine for the language L equals to 0 1 star 0. The input on the tape is 0110 with the blank symbol on both sides. The machine starts in state Q 0 and the head reads the first symbol which is 0. When the machine is in state Q0 and reads 0, it writes X, moves the head to the right and goes to the state Q1. This marks the first 0 and moves the machine forward. Now the machine is in state Q1 and the head reads 1. When the machine is in state 1 and reads 1, it writes Y, moves the head to the right and stays in the state Q1. This means the machine is marking the 1 and continuous scanning. Again, the machine is in state Q1 and it reads another 1. When the machine is in state Q1 and reads 1, it writes Y, moves right and remains in state Q1. This step repeats for any number of Y in the input. Now the head reads 0 while the machine is still in state Q1. When the machine is in state Q1 and reads 0, it writes X moves the head to the right and goes to the state Q0. This confirms the ending 0 of the state. The machine is now in state Q2 and head reads a blank symbol B. When the machine is in state Q2 and reads blank, it keeps the blank and moves right and goes to the state Q3. State Q3 is the accept state. Since the machine has reached state Q3, it halts and accepts the input state. So the string 0, 0, 1, 1, 0 is accepted and it belongs to the language L. Now let's look at a rejection case. When the machine is in Q0 and reads 1, it moves to the reject state. Also, when the machine is in Q0 and reads blank, it moves to the reject state. This is because the string must start with 0 to belong to the language. In this case, the machine is in state Q1. When the machine is in state Q1 and reads blank, it moves to the reject state. This means the input contains only 0 followed by 1s, but no ending with ending 0. So the string is invalid. Here the machine is in Q2 state. When the machine is in Q2 state, reads 0 or 1, it moves to the reject state. This means there is an extra symbol after the final 0, which is not allowed. This slide shows the formal 7-tuple representation of a Turing machine. All the transition listed here exactly matches the step we just explained. Therefore, the Turing machine correctly recognizes the language L equals to 0, 1 star 0. That's all from my part. Now I will invite my next teammate for further explanation.
Now I will explain example 2. The language is. This means the number of the 0s must be equal to the number of 1s and all 0s must appear before 1s. Here is the input is shown on the tape with blank symbols on both sides and the machine starts in state Q0. In step 1, in this step, the head is at the first 0 and the machine is in state Q0. According to the transition rules, when Q0 reads 0, it replaces it with X and moves right, going to state Q1. X means this 0 is already proceeded. Now the machine is in state Q1. In Q1, when it reads its another 0, it keeps it unchanged and moves right. This allows the machine to reach the first one. Here, the machine finds the first one in state Q1. When it reads 1, it marks it as Y and moves left, entering state Q2. Y means this one is matched with a 0. Now the machine is in state Q2. State Q2 moves the head left across symbols to return towards the marked X. This backward movement prepares the machine for the next cycle. When Q2 reads X, it knows one pair of 0 and 1 is complete. So it moves right and goes back to state Q0. Now the machine is ready to process the next 0. The same process repeats, another 0 will be marked as X and its matching 1 will be marked as Y. This looping continues until all symbols are processed. At this point, the tape contains X and Y symbols. The machine skips over already marked symbols and only processes unmarked ones. This ensures no symbol is counted twice. Now we see the machine moving right across Y symbols. This means all zeros have been matched and the machine is checking the remaining tape. The machine moves left again to confirm there are no unprocessed symbols. This part of the final verification. Now the machine enters in the state Q3. State Q3 is used for final scan to ensure only Y symbol remains. In state Q3, the machine moves right over Y symbols. If anything other than Y or blank appears, the input would be rejected. When the machine reaches the blank symbol B after all YS, it's confirmed the input is valid. Now the machine enters state Q4. State Q4 is the accept state. This means input string belongs to the language O to the power n 1 to the power n. This slide shows the formal 7 tulip definition of the Turing machine. In Q, it states all states used in these machines. The second one is input symbols, which is 0 and 1. Tape symbols, including X, Y, and B. And Q naught is started, and which is Q4 accept state, and the other is transition function, and there are a couple of transition functions in this example.
Assalamu alaikum. My name is Faisal Hussain Khan, ID 2411503. So I'll be talking further. So as for real life examples, we can use the Turing machine, such as compilers and interpreters. These in this case, Turing machine performs sequential rule-based translation of code. In operating systems and the CPU, the CPU executes instructions in discrete, state-driven steps. In robotics and automation, follow deterministic step-by-step instruction sequences. For all programming languages, all high-level command ultimately map down to the elementary read, write, move operations of a Turing machine. For the next slide, why the Turing machine matters today. Because this is the foundation of modern computers. Every computer is a universal Turing machine, and it defines the boundary of computability. It allows us allows us to prove what problems can or cannot be solved by a computer. It is standard for algorithm analysis, provides the hardware independent benchmark for measuring efficiency, and it is the basic for complexity theory, used to classify based on resource requirements. So as for conclusion, we can say that the Turing machine is the most powerful computational model possible. It uses in universal simulations. It can simulate all other models of computations. It is the foundation of computer science. The church-turning thesis confirms its role of theoretical bedrock, formally defining the algorithm, and it is the pinnacle of modern reality. Every modern computer is fundamentally a universal Turing machine. Thank you for your time. Assalamu alaikum.